Welcome to today's webinar. The topic today is modeling and design of CLT panels in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the website, German and English webinars, customer projects, and so on. I will be the moderator today. Bastian will be the presenter and Gerd will together with me answer your questions, but both colleagues can introduce themselves.
All right, thank you, Andreas. My name is Bastian Kuhn. I'm responsible for the development regarding our timber products, and I'm happy to show you our CLT design today.
Yeah, hello, my name is Gerhard Rehm. I'm doing more or less the same like Bastian does, so development and customer support. And yeah, I'm happy to answer your questions today.
So I'm muted. Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. For all who participate such a webinar the first time, I would like to introduce or describe how to ask questions. You can show or hide the control panel with that arrow here, and then you can enter a short question here, and we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, Bastian will say something about the concept of multi-layer surface add-on in CLT design. The main topic is the design of CLT panels, plates, and walls. And the third point is hints for modeling and results evaluation. Then I hand over the screen to Bastian and he can start.
Thank you. What I want to show you today is actually separated into two smaller models. The first one is based on a customer project, which we will just model from the scratch and design. It's the Brook Common building, so that's 18 stories and 53-meter high, standing in Vancouver in Canada. It's just because it's a perfect structure, and we will actually design one story of it. Therefore, we directly go into our new program RFEM 6 and will create a new position. I don't want to lose too many words about how you arrange models, and also we are not doing a theoretical introduction into the design process, but okay, a few words can be talking about how it's going to be, how the general model is going to be defined and how you can assign it. So first of all, we give it a name, that's webinar CLT 2D plate, for example. And in the second register, we are actually activating the add-ons or what we want to design. So what do we want to need to do today? Of course, we want to define a CLT floor. For this, for generating the stiffness, you would need the add-on multi-layer surfaces. It's written in the brackets there, e.g. laminate and CLT. So it's not only for timber, for CLT, it can also be used, for example, for glass and several other products like carbon fibers and so on. Wherever you have several layers of material, of any kind of material, lying one over the other and generate a stiffness from it, this is the add-on that you would need in our portfolio. Then when you have created the stiffness, generated the model, and so on, what I will do now directly with you, in the second step, you would have to design it. And as today we are designing CLT, this will be the add-on timber design. So what's possible now in timber design, if you compare it with the older software RFEM 5, is you can also design beams and surfaces. In the RFEM 5, the Timber Pro, it was only possible to design beams. So this is now the big advantage in this add-on. And of course, you see it here, it's not ready right now, but when you want to design glass, you would need the glass design additionally to the generation of the stiffness here, the multi-layer surface. Okay, we are not concentrating on load design or creation. That's why we switched that off and jump to the third register standards, as we want to design for timber, so for CLT. And we are in Germany here. I'm using the Eurocode with the timber annex in case I would be designing in America, Canada, Switzerland, or what else. I would have chosen the other standard. I can keep the global national annex, but of course there are for each country in Europe several national annexes you can choose. In general, what you are doing with this annexes is that you are or can assign deformation coefficients, the KDEF there. So in this case, I'm designing in the moisture class 1 and therefore use KDEF 0.6, which is already predefined. But in case I want to use another value, I can for sure choose that there. Okay, timber design, it's the same what counts for the load generation, and therefore we can skip that now from the explanation. Okay, then we are in the screen of RFEM 6 and directly will define the new thickness. Sorry, I wanted to start with a blank sheet, therefore I wanted to delete thickness and material because I want to show you directly what you have to do. So if you go in here and want to define a surface, you at first create a new thickness type here. And because that I have activated the add-on multi-layer surface, you have here a thickness type layers, what we will be using here today. So when you choose that, you see that thickness and so on can no longer be introduced in here, but a second register is opened where you can define layers. There you can also directly go to the material database and choose an orthotropic material model. And if you go to the library, you can see that we already have a few producers there. So there's Binderholz, Haslacher, KLH, Züblin with the Legno itself, Stora Enso, and so on. I will be choosing directly Binderholz with the BBS XL because I want to show you what exactly this is doing in here, because now I've chosen this material and it took now directly from the database the correct strengths which the producer, in this example here Binderholz, gave us, especially the verification or the strengths for the shear stress verifications are something where you do not have any values from standard. And so then if I had chosen an ordinary C24 material, I did not even have this strength here and would have to assign them. Okay, so now this is predefined and ongoing. It also made a stiffness of 12,000 Newton per square millimeters in the X direction, and in the Y direction it is 0. I said it already, we don't want or we cannot give you today a theoretic introduction into our design therefore, I will afterwards or during the modeling process, I will show you our homepage where you want to take a look into the manual, and we offer also special trainings for that, what I will also want to show you. But now, just what I say, in X direction, it's 12,000 Newton per square millimeter, and in Y direction, for one layer, we have a value of 0. But yeah, if you know CLT material, it's made of several layers. Let's say in this case, we are taking 5 layers, and you have the stiffness in these layers here as well. You know that the middle layers of a 5-layer plate are always turned around 90 degrees with their stiffness, and therefore it is not 0 for the whole plate, but it is the stiffness is 0 for one layer. That what is maybe important. For graphical reasons, I'm now choosing the same material once again. So go directly back to the database, choose this material here as well, and here, and give it also a red color because I like the difference between red and blue. So that's here. Here I'm exactly using the same material model. There's no difference in between this. So also the material values, they are the same. It's, as I said, it's just the graphical reason. Yes, you see now that it's red, and it also in the rendered material afterwards, it will also be red and blue. Yeah, just a personal point. You can also save this setup to a database. So of course, we could use it for the second model that we want to create today. Therefore, we name it now Webinar CLT or whatever name you want. And then later on, we can load it from a template in here. Ongoing, what I missed now is the stiffness reduction, because when we are calculating with the shear stiff transfer of the load, and because it is like this, we have to reduce the shear stiffness in some parts. So the drilling stiffness K33 and also the in-plane shear strength K88. I will also give you a link or show you a link later on where this is described more detailed as well. Here on the bottom of the third register that has now opened, I have options especially for CLT design. I could use here glue at narrow sides. The reason for this is that most of the producers are gluing their CLT on the narrow sides, at least for the production process. They do not assign it for the stiffness, because this is in the values that I just showed you. The EY, you saw it, is still 0 there, but they are using a little bit higher shear strengths. But stiffness, because of cracks in the boards, they are not increasing it or not regarding it. So therefore, in the first model, I will glue it at the narrow sides, and in the second model, I will show you the difference in between. What happens when you switch it on or switch it off. Okay, but for now, we're using it glued. Okay, say okay, and one more time, okay, and now we are in the screen, use the origin of 0, 0, and then we want to take it a width of 55 meter, and the height of each plate should be 3.5 meter. Of course, it is, I know that it's not possible to produce a 55 meter long board, but there are options to calculate such things also stiff for the rotation. And I want to have several boards with a width of 3.5 meters in the Y direction, and that's actually where the higher force can or should be regarded. I'm using the dynamical size of the grid and will now copy it the system 3 times into the Y direction with a value of 3.5 meters. So then it's here, and I want to show you now why I used the rendering in there. Therefore, we switch here to the view screen and then say surface. So see it. No, now you cannot see it. Sorry, I have to go to model, solid model, surface, filled including thickness. So, and now you see that's the only reason why I did that, because you can now see each layer in here, and it also becomes, I think, much better visible how the layers are oriented. We have implemented here in the surfaces a so-called orthotropic directions, because what the material model that I showed you or I explained you is an orthotropic material. But if you switch that on, you see there's happening nothing. You see nothing. Why is it like this? Because now the layers are oriented in 0 and 90 degrees. And if you want to see how they are oriented, you have, first of all, you have to switch off the rendering, but then you can see how they are oriented. And if you switch the indice on, you see that the layers 1, 2, 3, and 5 are oriented into X direction, and the layers 2 and 4 are oriented in the Y direction. So my main stiffness is in global X direction. That is what is important in here. Okay. So that's the model. I can right now actually switch that off and say now divide these 2 lines by 3 nodes, because these are going to be my stiffening cores in the center. So they are made from concrete, and I'm just attaching to this. Now, that's how it was assembled in the building in 2017. And then so they have a width of 6 meters, and the second core is at an origin of, let me take a look, 37 meters. I'm not using the exact values from the building there, but yeah, just to have it close to the structure that we have in there. So this 3 nodes I will also just copy 1 times in minus 1.5 meter. Say okay, and then I have it there, and then I will draw a few lines in here and there. Oops. And this one I will be copying via drag and drop onto the right side. Okay. I will connect the lines in here, and then it's okay. And then a very nice feature is, or a very nice function, not a feature, is if you go right click in here, you can divide the surfaces by integrating lines. And now you can just delete the surfaces which we do not need. Okay, the facade is running on the outside of the structure, and the supports are laying in the inside. Therefore, we are copying the outer line now about a value of 0.4 meter in the Y direction, and this one then also on 13.2 meter as well, also with 1 copy. I will take the inner lines, and before I do that, I have to look for the origin of these lines, which also works via the display navigator lines, line orientation. And now you see that this line is not in the same orientation. Therefore, I will use reverse line orientation in here. And now that I'm just in this dialog, I can also take a look if my line axis system is similar. Of course, now that I changed it, it is important later on in order to define the slip in between surface number 1, 2, and so on. I will do that, explain that when I'm doing that. But first of all, for the supports, we want to divide the lines in here. Say, okay, divide line distance from the end is 50 centimeter. Still forgot one. Sorry for that. Divide line with a distance at the end 0.5. Okay, it's not happening again because I have to do it here as well. So divide distance and then at the start also 50 centimeters. Okay, now this is how the supports will be running, and of course that are not enough supports. We need more columns in the structure. We have now also to divide the line by n intermediate nodes, and what's also a very nice function in RFEM 6, or which is has been improved compared to RFEM 5, is that you can now create a line without dividing it. You could do that in RFEM 5 as well. That's not completely true what I'm saying here, but there are more options for it right now. So I'm copying it 11 times, I think. Yep. 11 times without dividing it. Yeah, that's all. Sorry. Okay. Now the structure is nearly there. I have to just interconnect that. Actually, I could also, that's not really necessary. I could also have left it like this. And for the inner line in here, of course, you also want to have the nodes copied to there. Shift function is deselecting what you do not want to copy. And now I'm doing one copy of a value of minus 3.1 meter, and now they are there. Okay, now I introduced it already several times now, and the question is, well, how can I now define a slip in between this structure in here? And that would be done with a line hinge. A line hinge is also improved very good in RFEM 6. If you remember RFEM 5, you had to do a lot of line hinges on such a structure, and now it is possible to do it only for one object. But still, you would have to define a slip here in UX and UY direction. And therefore, it's the first time I want to jump out a little bit, the first time for this presentation, what we are doing here today, and want to show you, well, a very, very simple calculation in Excel based. I just want you to know how I get this value and not grab it from heaven or somewhere. I'm calculating a slip in between the two plates in here based on some very simple equations. You see it here, K there equals the density, height times height, diameter of the connection, this times screw divided by 23. That's it. And it gives me now for a screw a value of 2,576. And now what's always important in your design process is actually how much connections per meter you can assign in there. So if you say now in this example 3, it will give you a stiffness of 7,729. If you use 4, 10,000 and so on. So the equation is very, very simple. You only use this added with this. Okay, that's, sorry for this little excursion, but I wanted, as I said, not just present it as heaven sent. And if you have this value for the slip modulus, you can go inside our global parameters and name it somehow, in this case, K there. And in unit groups, you already have a lot of values that you could use. And we want to have line spring constant, and this gives you this value in here. Okay, and insert, and now it's there. So that is now not really a big step, because if you only have this, what does it bring you? Because now you design the structure and you find out, okay, 3 connectors, that's not enough. I need to have 4. I need to have it more stiff. Then you always have to jump inside here and have to define it. And also for your documentation, the printout report, you have like nothing. So how can you improve that? And if you go to this info box in here, you see there's the option to insert object properties. And there are now also very, very many options that you can do. But we just want the simplest one of it, line hinges and comment. Say okay. And you see right now, it's a simple Java script function that I'm using in here. But it has an intelligence behind, because it already tells me, okay, what you're doing here is an error. It's something wrong. And what is wrong? Okay, I need to tell the software what object I want to assign the comment to. So in this case, that's the object 1. I just have to type it here. You see it here in the list on the left side. And I forgot the addition in here. So, and now you see, well, the value is still 0, but I have something in here. In order for my documentation, I'm using this little slice in here. That's just, yeah, something you need to Google and will find out directly. So if you say, okay, nothing changed, that's a little bit annoying. Why is not sending that value that I want? Because you have to define it here in the comment. And if you see, say 3 connectors, or whatever, if you can also say 3 screws or whatever, it is, first of all, this comment is taken to the printout report. I will show you after we did the design. And now if you find out during the process, okay, 3 is not enough, I need to do 4, or it has just to be stiffer, you can just define it here, and it's in real time changed in it. Well, of course, right now I know 3 is more than enough for this structure, because the horizontal load that I'm assigning here today is not that big. But yeah, that's something you will find out always during the design process that you need it. Okay, so then second, we do it also for the Y direction, because according to the spring laws, you need to have it in the plate area for X and Y direction. Rotational spring constant, with newer researches, it is also possible to define a value in here, but right now I'm leaving 0. Of course, you could have something similar, like I did it for X and Y direction, also for the rotation. And Z direction is not necessary to define any kind of slip. Okay, I screwed it a little bit up, but it does not matter, because I left the dialog. I did actually not want to do that. If you jump into types for lines, line hinge, it gives you or me the opportunity to show you the advantage of it, because in RFEM 5, you would now have to open the dialog once again and also define the line hinge once again. But as this is an object now here, I do not have to do that, and can now do it correctly and choose the surface and assign it to this line, this line, this line. So wherever I'm assigning it, I'm defining a slip. So in between this plate and this plate is defined a slip, and this plate and this plate. And now is missing a slip between this plate and this plate. And yeah, once again, back in RFEM 5, you would have to define it, the whole stuff once again. But in here, I just can click there, and it's absolutely no deal. So that's, to me, a big, big advantage of the new workflow. Okay, it's a little bit small. Maybe I will just increase the size a little bit just to see it in here, and go actually in Z direction again. That's now defined, and I can define the supports that are presenting The columns underneath, they are very simple. They are just using force in UZ direction and nothing else. Say okay, and assign it in here and in there and there and there. That's also, to me at least, a little bit small, and we can also maybe just a little bit increase it. Okay. What else do we need? In this case, when there's horizontal force, it will just move away, and we need to define the line supports from the core, and that would work via line supports, define or edit the existing ones, and we use actually the same intelligence here, but for local systems, and because we want the force just to be acted in longitudinal direction of the line, I will just release UX or just give the slip to UX UI. I will complete the release. That's how I want to do it. And then I'm using the same like before, using Kaiser. Do not make the mistake from before. And now if you go in here, it's obviously not line hinge what we want to do now, but line supports. And they're also just a simplest function comment. You see in here, you can do a whole bunch of stuff with this. So you can have diagrams with forces coming from other directions than UX and so on. That's all included in here. But yeah, once again, we use the simplest one. So with line support 1 point, same function like before, 0.1 and this, and no error, and then we just type it here, say, what did we write? I forgot it. 3 screws, I think. And now we have it here. Yeah, works the same way. Yeah, trust me, it is like this. All right, 3, this. Okay. But we need to assign it to the lines. That I should not forget. So where do we want it? There, and there. Choop. And of course there, and there. So the model is now already there. Maybe we want to have some dimensions for it as well, just to have it, a little bit nicer. And maybe we are actually directly starting the printout report, because there's all something quite nice in the new RFEM 6 that I want to show you once we have the dimensioning ready. So okay, sorry, just maybe you would do it different when you are making the design of it, but for this I think it is now all right. And we print this graphic to the printout report, because in RFEM 6 it is possible to have the printout report opened when you are working on the model. And we will do that. We will maybe use it window filling, and maybe not we take maybe 40% of the height. Save and show. I did not choose a printout report. I don't know. Actually, I should have selected the printout report in here. Here. So, and it works in the same way like the material database before. You have here templates, what you can choose. And I actually have created one for today's webinar, especially where I selected and deselected a whole bunch of stuff. I think we will now assign it and then go back to the design process. All right, it's generating it. Gives me time to drink coffee, a small one. Okay, now it's there. Actually, I could have opened it, but so we're not doing a webinar about the printout report today, but of course I want to show you what kind of points you can implement in there for CLT or for timber design in general. Okay, so but here's now the model, and that's it so far. And we go back to the design process and introduce the load. Deactivate all dimensions, so because I don't want to see them any longer. And introduce the load. So first of all, we're doing a horizontal force just to have a deformation then in Y direction of 1 kilonewton per meter. If you have looked for the building, it is standing in most of the highest earthquake areas around the world, so there's probably more force than 1 kilonewton per meter. Also from wind, there's probably more force. But yeah, just maybe we are in the ground floor here and just have some small force. Yeah, we also take a small value in the load case 1 from self weight and say also, okay, we have that here. And now we define for each plate a live load. So this will be 5 times. Say, okay, and now also one of the advantages, if you compare it with RFEM5, and yeah, I'm worked long years with RFEM5, I'm still comparing it. But if you are new, you do not have to compare it. In RFEM5, you would have to define the surface on load case 2. Say, okay, leave the dialog, and then choose the second, or in this case, the third load case, assign it there, and so on. This is, as you see in here, also no longer necessary. All right. And last but not least, this one. Okay, so we can now also control if we did that all correctly. It's all correctly. And go into the load cases and combinations. Yeah, I said it, we're choosing timber here as a standard group, and the design situation, I would just use quasi-permanent. The other ones I'm not interested in, and I'm calculating according first order theory and automatically create my combinations for that. And now they are here, say okay. And now I could have started with the design in the add-on timber design because I have activated that in the basic datas, but I have to show you the objects that you can or should take care on. If you once again compare that with RFEM5, there you have the design add-ons Laminate and Timber Pro, and all the things what you have defined in these add-ons are now moved in RFEM6 into the objects. In this case, we are designing surfaces, and so in here you define it, yeah, in the surface. First of all, if you look for the deflection, yeah, you can choose deformed, undeformed system, but that's not what I'm up to. I want to show you a plate is always a little bit problematic when it comes to no clear deformation where you should consider a reference length too. So the distance between this support here on my node and this is actually 4.5 meters, if you remember what I did by copying them. But how do you want to regard it with this other side? And therefore I choose 5 meters because I'm choosing the difference between this point here, and you cannot see it now in here, but the other point there. So to me, that is now on the safe side. And if deformation gives me problems, I anyway would have to do a more detailed deflection analysis. Okay, that's, I hope, explaining it a little bit. Ultimate limit state configurations. We have a combination for ultimate limit state configuration, and therefore, of course, we also have to look for the objects. The first two registers are for members, and the third one is for surfaces. maybe most interesting for the designer is that now for CLT, it's also possible to consider a system strength factor. So that would be possible in here, and then you could increase it to 1.1, for example. The other ones are not important for surfaces, and therefore I'm not explaining them. Serviceability configurations is also now divided into members and surfaces. You can there just do nothing else than comparing limits or defining limits for the comparison of the deformation. I will show that afterwards in the verification. Now the third configuration is for fire resistance. Once again, the first one is members, the second one is surfaces. Everybody who has been working with FM5 is now maybe happy, because he would think, okay, I have now also verifications for fire resistance in FM6, but we're working on that. It's also not far away, but right now we are not doing a design of the surface, but we will calculate the burning rate. So the reduced section height of your plate, we will calculate and also give you as a result. And you can, of course, define a lot of stuff in here, and that's already an advantage compared to FM5. But just as a note, the design is not ready for this fire resistance right now. Okay, here you define the service class. Usually it is service class 1 or 2, so dry or moisture. In our case, we have service class 1. I think that's probably the most common way for 90% of the structures. Okay, so that's now done. Enough explanation. In first step, I can also just calculate the ultimate limit state, because serviceability state I could design when I'm sure that everything else is working correctly. Actually, see what I missed here. Here's missing a support there and also there. Yeah, maybe do some checking before we start, but the rest looks great. And I will start the design process and will give you small explanations about how the stiffness is generated and what is actually done in there. That's what I wanted to show you right away. Okay, that's opening now on the other screen. Ta-ta! Hold on. Oh, that's confusing me. I hope you see it now. Can you see it now? Maybe my colleagues can give me, Andreas, can you see now the presentation?
Yes.
Perfect. Okay. Yeah, if you remember how we introduced the layers in there, just a small theoretic explanation to that. We did define a stiffness of EX and EY, and also a Poisson's ratio, and of course a shear modulus. And that is now defined in every layer. From each of this layer, we are calculating a global stiffness matrix, which is then exported into RFEM. And in RFEM, we calculate deformations, stresses, and inner forces on one plate, not on the whole layers, but on one plate. And these inner forces are then transferred into every layer of it. That's actually the theory behind that. So let's see if we can get the RFEM6 back now, or maybe the homepage back. I don't know. Right now, my screen is a little bit black. We can take a look. Transfer. Yeah. Okay, there you go. Well, that's now. I did the webinar in Germany language on Tuesday. There are problems with my screen. I think that's now based on the on the software. Sorry, go to webinar. I don't know. Okay, this is this. We can take a look on the results in the RFEM 6. Hold on. How did we name it? I think it was this one. Yeah. Okay, so you see, we have now an overloading, which is not the desired behavior because we want to be green and we want to be smaller than 1. But if you look into the details of it, you can see that the overloading is just in a very small spot in here. I can actually switch off the nodal supports. They are not necessary to me here anymore. There. Okay. And if you realize that in reality, there's not standing a needle underneath this point in here, but a column with a diameter of something, let's say 40 centimeter or something else, it's obvious that you should not take the force in this spot in here, but you should take the force somewhere outside. And I will actually show you how to do that. In the literature. You will find this described as a so-called punch-through verification. But before we do that, we go and take a look at first into the verification itself. Via double click, we go into the details of it. You see now that in RFEM 6 we have quite a nice form or equations shown here, and they are also filled with values. So you have the shear strength shown here. You have the option to take a look onto the ratio over the section itself. Or you see here now, these are the several layers that we have defined. You can switch it to stress and take a look into it. So sigma x, the bending stress, you see that there where you have a high stiffness and the high loading, you have a higher stress. So that can all be compared into here. And of course, okay, we also want to take a look at the shear stress, and they are usually in the center of your section. That's the same for beams, counts for plates as well. Okay, you could also print such things for, no, maybe not this one, but maybe this one into the printout report. It's opened on the back, so we can just say, yeah, take it like this, maybe a smaller height. Actually, that's okay. So we just say okay, and then it's already in the printout report, and I do not have to take a look on that. We will do that later on. Say close, and or I could have also left it open. It does not really matter. What else is new and possible and quite or very much nicer than it was or has been in the RFEM 5? If you go to the result navigator here, you can see that first of all, you have now a ratio envelope of all stresses that are in here. You have them here and can print them to the protocol direct, or use them for your analysis as well. You can separate between several stresses and also between several, okay, we just have one layer in here, but several layer sides, for example, top, middle, and bottom. Actually, it was not true. Here, I can choose the layer. So for shear, you would probably use one of the inner ones, and for bending, you would probably use the outer ones. That's the first nice function. If we jump back to the static analysis itself, for the connection design, we have, first of all, when you go to the static analysis, you can see there the global deformation and compare it just to get a feeling of what's going on in here. You could also here for each layer take a look at your stresses and also for your strains. That's for some cases quite interesting, I think. And if you just let's say if you compare sigma x on the on the negative side of the surface, you see that there is a value on the top of 3.8 here as a maximum, and if you go to the middle, it actually is quite low, the value. And if you go to the bottom of your section and choose sigma x on the positive side, it gives you the same value as you had for the top side. So that's also something that you could use for your analysis. Ongoing, what I said, first of all, we want to look in static analysis for the connection design, and therefore we have also options here. First of all, the more simple verification of the connection is in the line support, because there we have just a slip defined in x direction. So this is now the force that you need to connect with your connectors in the x direction, or in the longitudinal direction of your line. But also for the line hinge, you can take a look at the force in here. And this is now also the force that you have to assign between this panel and this panel. Now let's take a look where the maximum value is. Well, it does not matter. It is here. It's quite a smooth value, and you do not have any singularity effect in the connection itself. But nevertheless, from time to time, you will face this problem. And therefore, here in the result diagram, maybe we will switch to one of the more bigger ratios in here. In the result diagram, you have the option to smooth these values as well. So you can also here say force, normal force. And if you look now for the values in here, some way say, okay, 10 meter, 12 meter, that's where I'm average, or where I would be able to average my results. And if you do that in here and say, okay, whoops, start 0 and 12 meter, let's say it like this, you see that you have the force that's has to be attached by connectors, whatever, is 9.5 or 0.464 kilonewton, and per meter you need a force of 0.789. So also this is probably something we want to have into the printout report. So we as well will there say, okay, maybe we will not use the full height, but something like this should be in there. And we also say, okay, and leave the dialog. Also, this result diagram, I would not need to close. So if you work with two screens, sadly, in our presentation tool, we do not have the option to show two screens at the same time. But yeah, this also does not need to be closed. Okay, but back to the design of the timber. So when you look for that, we still have the overloading in here. How can you get rid of that? It's actually similar to what I showed you with the smoothing of the result diagrams. It's just called differently. It's called insert special object surface results adjustment. This is just for smoothing your result. So now if we say we have a column of a width of or diameter of 40 centimeters, it is definitely possible to use a dimension of 60 centimeters. I will show you the reason right away. Sorry. Okay, I'm choosing all surfaces in here, and I will define it on the origin and press OK. Not on the origin, but on the first support here. So you see it. I have not shown the supports now here because I've switched them off, but trust me, they are there. So this and this. I'm just using grab and what's it called? Grab and drag. Oh, I forgot it. Sorry. So then I will copy these areas here. Let me take a look how many times I need to do that. I wrote it, so 12 times we need to copy it because we do have 12 supports in the X direction and by a value not in Y but in X direction of 4.5 meters. That's the span we have in here. So, all right, go to that again. You see there's the axis system displayed for this. We do not need this. That's nonsense for our NDAvers in here. It also makes it not looking that good. So we will switch the axis system off. And now we will calculate it again. And as I'm sure that the design process for me is finished now, I'm also selecting the SLS design to be done. And go back to our homepage in order to give you the promised more theoretic explanations. So one thing that I missed when I did show you the definition of the layer and the stiffness reduction was an explanation how the factors for K33 and K88 are calculated. And my colleague Gerhard, who's now answering all your questions, we can actually, when I did this explanation here, we can take a look if there are some questions we maybe should want to discuss to the audition. So he has a very nice Excel file here, which gives you also the option to calculate these values. And of course, when we have a database for the producers, we will also use the factors that the producers are offering us. So you do not have to calculate that for all the setups in there. The stress, actually, I wanted to show you later on. That's the online manual. It's not ready yet. I'm working on it. So there are actually still a few points missing in here, but yeah, what you could have there, for example, a lot of customers on Tuesday's webinar asked us, is it possible to display the stiffness matrix? If you remember in the second point, the stiffness matrix for the global plate, can I display that? Right now, it's not possible, but you could download on our homepage or in the online manual a plugin tool, and if you use that, you still can see the stiffness in this example here. So D11, that's the bending stiffness for this example that we have here in the manual. I also said that we cannot give you a complete detailed theoretical introduction into the design of CLT. If you want that, we are offering online training. You will find it here also on our homepage, online training. And if you go program version, training type Eurocode 5, that's actually the timber. This is in March for English, the 16th of March. If you like the building that I showed you here, so this Brook Common building, I did a webinar in September last year where I also showed the whole design process for the complete building in it, so with all stories inside. That's it. So now let me take a look if there were questions asked very often. Yeah, okay, there was a question, my colleague just showed it to me, that probably occurred more often. And the question was why I defined 4 load cases for the system here. So I did for the live load. So I have it on the outer plate and then one of the middle. Oops. Oh, it's not jumping. Now it's jumping. Just took a little bit of time. So and here, there, and then this one here, and this one here. I hope it can be seen correctly. Yeah, in the theoretic world, you would have to define a live load in the first field from this point to this point to this point to this point, and then this one should be empty, then this one should be loaded, and then this one should be empty, or this one should be loaded, and you need to do it in X direction and in Y direction. But for the sake of simplification of today's webinar, I just use this, I only know the German word, it's a Schachbrett loading introduction. You can Google that, I don't know. Therefore, I'm just using it in Y direction, not in X direction. Because if I would do that also in X direction, I have, I don't know, 10 or 20 load cases, and the calculation time will just increase. You can compare it with a continuous beam. If you have 2 fields, you also have to introduce the live load on the left side and on the right side, because for the middle support, the highest force in the middle support will be with live load left side plus live load right side, but the highest field moment is with the force on the left side, if it is the longer span, for example. Okay, so hope that's clear. And now we can take a look at the results and then just create a printout report and we are fine. Results good now. So the overloading of 1.1 is now changed into a loading of 0.8. Of course, you should make a finer mesh in here. So if you look in here, you see that the span in here is just smoothing it about this area. So, but in general, that's how it can be done, or how to regard the punching in here and how to avoid this overloading. Yeah, I showed you this verifications already. Therefore, I'm not losing too many words on that. Maybe we just go via double click into this verification of the serviceability and also print to the printout report. You see, it's the same equations like in the formulas before. And now we go into the multi-editing of printing. So I already have a model put into the printout report, so I'm not doing this anymore, but I'm using the 40% of the structure. So we do not want to have this, but we maybe want to have all load cases and maybe also the current view of the add-on. Maybe actually, I don't know. It's probably a lot of results. Okay, we can try to put it in there, and we want to have that window filling. And now we can open the protocol. I must see it's somewhere on the other screen. There it is already, I think. Oops. Hold on. Yeah, there it is. Okay, now it's loading all the pictures into it. You see it on the left side, but yeah, as I said, it has been opened all the time. And now it's printing the pictures of the load, the results of the lines. What else did we put into it? Details and stress verification. Well, we can take a look what is in there. Yeah, I'm not going into every detail, but into some details. So first of all, yeah, the good point is that for the documentation purposes, you have now the stiffness here, and you can write additional text into it. What was asked for quite often. Here's the model. Here you have the live load, the self weight. You have the live load of all these load cases. This result diagram we have in here, it's also quite nice to have for your analysis. Yeah, this diagram is printed in here, and also the deflection of it. Okay, that's the bigger model, and I'm now showing you a very small model which only should take about less than 10 minutes, let's say. We name it wall and say add-on multi-layer timber design as well. It's the same as I did before. Nothing to say about that. And we take a very simple structure now, go into this other area and say here once again, we can now choose the material, what we have defined. It's already predefined, but of course, it's also the one what I saved. It's the same material and just take it over. Now stiffness reduction, I want to show you the difference. If you remember before, I only had reduced these factors here, but kept it glued at the narrow sides. Now, if I change that, it will actually do two additional verifications. And now the last time I have to switch to the home page and show you the stresses, what I just announced. So if you have glued at the narrow sides, it will only do the verification of I don't know if the English word is really thrust cross section. I have to look that up. So but it will then not do the verification of the netto section and also not of the torsion. So if you look into these two equations here, you see that the width has quite a big influence in all the equations. And now we get back to the program. It would be possible to also include gaps. So that is also then regarded for the verification. Also for this, when we have the producer material databases, we will assign here the widths that the producers are giving us. In the standard for Austria, it is recommended to use 8 centimeters, but a lot of producers are also calculating with 10 centimeters, which is also okay, I would say. So yeah, default value will be 10, and you as a designer have to say what you are using here. But yeah, I would say if you use 10, you do not do too much wrong in here. So okay, we make it a wall, give it a little opening, yeah, assigned here by this, just to have it symmetric. Oops. And in order to see something there with the shear problematic, because that's the only reason I'm showing you this example here, we make it quite narrow here on the top. And because it is this kind of narrow, I have to refine my FE mesh in order to have at least 2 elements over the height of this little spandrel in here. We'll define it support on the left side. Come on. Yeah, we'll just clamp around for the torsion, just that I do not have to define so much more. And right side, I have to define a new nodal support, movable in X direction in here. Zack. tuck, and also give it some force on the top, and the force will be 2 kilonewton per not per square meter, per meter. And then I also will define a live load. Maybe the live load has to be introduced on the bottom because, yeah, usually self-weight comes from the roof, but live load comes from the story. And that should definitely be higher than 2 kilonewtons. So let's say 10 kilonewton per meter. All right. Okay, do a little combination. Of course, I know you need to do a deflection analysis for this very narrow spandrel in here on top. But right now, I just concentrate on, ULS, ultimate limit states. I'm not interested in this kind of deflection now in here. Of course, you could do that and say, okay, and now I will calculate. Okay, here, these are the design configurations. We're also not concentrating on this, but just that you saw it, that they are still there. And now we calculate the results of the timber. And now these two additional verifications are done. And I can show you the stress that is, yeah, calculated for this. You see quite a lot overloading. Why is that the case? Because I forgot to do the smoothing here on the bottom. So that's my fault. Sorry for that. I forgot it. And therefore you go to insert. And in this case, we're using quite a big one in here and say this, and this on that, and say okay, and then it has, of course, to delete the results, at least for the timber design via drag and drop. I would just copy it to the right side, and now I only have to calculate the timber results of it again, and now, yeah, it looks much better, magic. And what I wanted to show you, so this is the verification we already had before, but now additionally we are doing also the verification of failure mechanism 2 and 3. I think 3 is the more interesting verification. I don't know. That's really through just my personal feeling. So you see in here in the details that there you have the torsional shear stress of this value, and we are also doing additionally shear stress in X and XZ direction. But you see that, yeah, the introduction of this is very, very low. So the basic point of it definitely is the stress of the torsion. Okay, tau tor X, that's here. Of course, it's constant over the whole section. That's always the case for this kind of stress. And here you have it in the netto section, which is the failure mode 2. Okay, good. To me, it worked all nice, or quite well. And I will give the word back to my colleagues. I don't know if maybe Gerhard also want to say something for often asked questions, or Andreas just want to wish everybody a nice evening. Thank you.
Okay, thank you, Bastian, for your presentation. We are a little bit over the time. That's why I would not close the webinar immediately. I would like to show my screen again to show you where you can find the recording and the models that we presented on our website, dlubal.com. Under news and events, you can find the webinars. Those are the webinars in the next time that we are already scheduled. And that's today's webinar. And if you click on it, then you will find the recording here in the next days. And already the models, both models are already there. But you will get an email with a link to that page, also with your attendee certificate and so on. Okay, and yeah, if you don't use already RFEM 6, you can download the free trial version. RFEM 6, it contains all add-ons, also the add-on multi-layer surfaces and the timber design add-on and all other add-ons. And you can use it for 90 days. Okay, then, yeah, maybe a last hint when you leave the webinar, there is a small survey. Yeah, you can answer some questions and you can enter wishes for future webinars and so on. Yeah, you can score us. Yeah, it will take only 1 minute. It would be very nice if you fill it out. Just note that the worst score is 1 and the best score is 5. Okay, Ben, thank you for your attention. Thanks to Bastian for this nice presentation. Thanks to Gerhard for answering the question. I wish you all a nice rest of the day. Bye-bye.